how to draw a graph without GDC. So we'll start with this example. And we have the following information that we always need to gather. Domain, x bigger equal than -2, x not 1. X-intercepts, -2, 0. Asymptotes, x equals 1. And the derivative. You need to be careful a bit of the algebra. When I differentiate square roots, see how this square root is a denominator. So when I add here the two fractions, the common denominator, the square root will disappear from here. So that's a nice result that you get, a very neat one. And that is your first derivative. Now I need to collect all the information in the table that we are talking about. Let me start with first line. It's always x and always a domain. So the domain is from -2 to infinity, except for the point 1. So I'm going to draw a line vertical because 1 is not in the domain. First line is dy by dx, or f dash. Third line is y. Now I need to look at the sign of the derivative. And see, if you look at the domain, x plus 2 is positive. X minus 1 square is positive because it's a square. So the sign is given by the sign of minus x minus 5. This is bigger than 0 when x is smaller than minus 5. So minus 5 is before minus 2. Yeah, so I can conclude that this one is always negative. Meaning that my function goes down up to 1 and then again goes down. When x is -2, y is 0, I need to fill in the values of y for all the points there. When x is infinity, this is going to be 0. Yeah, actually I forgot the horizontal asymptotes. Limit when x approaches infinity, f of x, and if you factorize an x and cancel, you'll get 0. So practically that's limit x approaches infinity, square root of x bracket square root of 1 plus 2 over x brackets 1 minus 1 over x. So see how here when we cancel the square root of x from here and from here, we are left with the square root of x on the denominator, so you get 0. Okay? When you get to -1 from the left, so limit when x approaches -1, x smaller than -1, square root of x plus 2 over x minus 1, you will get square root of 1, which is 1 over 0 minus, because x is smaller than 1. So here is minus infinity. Similarly, here is going to be plus infinity. And see how minus infinity and plus infinity actually match very well the behavior of my function, because I say that the function goes down, so from 0 goes to minus infinity, from plus infinity goes down to 0. So now I'm ready to draw the shape. The domain is from -2 to infinity, so here is not going to draw anything, and 1 is not in the domain. Okay. It's interesting what happens when x equals -2. So I can start, how am I going to start the graph? So from here, I need to go down to minus infinity, so somewhere here. But the question is, do I go down like this, or do I go down first like this and then have a turning point? Have a point of inflection. It's interesting to look at the first derivative. So when x equals -2 in the first derivative, yeah, if you want to calculate limit when x approaches -2, value is bigger than -2, f dash of x, if you replace -2, you are going to get 2 minus 5 -3 over 2 times 0 plus times 1, or times, doesn't really matter, it's times -3 squared times 9. So this is going to be minus infinity, the derivative, meaning that the slope is vertical. So the slope is infinity. So your function will come like this. And then come next to this one here. Here is pretty clear that it will come like this. And that's the shape of your graph. What's interesting about that is that if you graph it in your GDC, it looks first that you don't really see what's happening here. But then if you zoom into your GDC, and see I zoomed in on the y-axis, I changed the y-axis from -1 to 1. So we can see at the point x equals -2, the graph has a vertical tangent to the graph. But still it's not an asymptote. The function is defined at x equals negative to the very 0. But the tangent to the graph, it's vertical. There are times when you can have a special function and analyzing the function makes the process easier. As for example, if we are asked to graph this function, we would know how to graph g of x equals x plus 3 over x minus 4. And then we know what transformation is the absolute value. So if we look at g, asymptotes are y equals 1, x equals 4, and the graph will come like this, right? So then the absolute value graph will be that one, rather than having all the process of differentiation. How about if we have something like this? Well, in this case, you can't really use any of the properties and we'll have to turn it into a piecewise function. So I'll say that this one is x minus 1 over x plus 2 for x bigger equal than 1, and minus x minus 1 over x plus 2 for x smaller than 1. Well, we can still graph y equals x minus 1 over x plus 2, which we know that has y equals 1 for horizontal asymptote, x equals negative 2 a vertical asymptote. So when we graph it, it will come like this. Right, and now for x bigger than 1, so 1 is here, yeah, the graph is unchanged with this one. For x smaller than 1, this minus here shows us that it's a reflection on the x-axis. So for a value smaller than 1, the graph will be a reflection on the x-axis, and it will look something like this. Also, I need to reflect the other branch. So the green one will be y equals f of x. How about if we have something like this? That's an interesting one, because we can treat it in at least two ways. I think we can write f of x equals x plus 2 over x squared minus 4 for x bigger or equal than 0, and minus x plus 2 over x squared minus 4 for x smaller than 0. Now, if we are lucky enough to observe that some expressions cancel, we get 1 over x minus 2 for x bigger or equal than 0, and minus 1 over x plus 2 for x smaller than 0. We need to add that the domain is everything except for 2 and negative 2. So here I can't have x is 2, and here I can't have x is negative 2. Now if I'm trying to draw the graph, it's a one that I should know. For y equals 1 over x minus 2, the vertical asymptote is x equals 2. So the graph will look like this, and from here to here, because I'm practically missing this part. For x smaller than 0, x equals negative 2. It's a vertical asymptote, and the graph will look like so. This one is my resulting graph. See, at x equals 0, the function is continuous. At x equals 0, limit when x approaches 0, if the value is smaller than 0, it's minus 1 over x plus 2 is that branch, is minus 1 over 2. From the right, the graph, the rule is 1 over x minus 2, so it's still minus 1 over 2. And f of 0 is the same, minus 1 over 2. So the function is continuous at 0. How about if we have something like this? Well, we can take the same approach with a piecewise function and write f of x equals x plus 3 over x minus 4 for x bigger or equal than 0, x is not 4, minus x plus 3 over negative x minus 4 for x smaller than 0. And then graph each branch. Or I can consider the graph g of x equals x plus 3 over x minus 4. I know this graph, and then I'm going to ask how is it related to the given graph. So x equals 4 is a vertical asymptote, y equals 0, so the graph will look like this. Yeah. And now see how f of x is actually g of absolute value of x. Oh, are you surprised? So what do I know about this transformation? Everything that is positive stays. The negative part disappears and is replaced by a reflection of the positive part. Yeah? Not necessarily here is smooth. I even don't think that it's smooth, because if I would draw this one very correctly, and it comes like this, let's say, yeah? When I reflect this one, it's not going to be smooth necessarily. Well, to check, I will need to check the derivative here, but it's very unlikely that the derivative cannot be 0 for sure. So then it will not be smooth. So here are some techniques of drawing graphs.